Okay, the first limit equilibrium method we are going to look at in detail is called infinite slope analysis. And this is a really simple method that can be used as a reasonable approximation for cases where you have a shallow firm strata that is parallel to the slope, or cohesion. It works. It's also a very simple way to deal with cohesionless materials. Sands and gravels, or any soil that has no cohesion, and this could be the controlling or the critical factor of safety in those cases. And we'll see this a lot even when we use slope stability software. There are cases where this will come up as a critical case organically. And again, no slope is truly infinite, but in terms of the derivation of the equations, we're looking at just a section of a slope that we assume continues up to the right and down to the left. And we're looking at a sliding block along the surface defined by that dashed line. And so if we do a free body diagram of that sliding block, it has a length parallel to the slope of L, a depth vertically of Z, and the slope angle is beta. There's a weight based on the unit weight and the volume of that block. There is a shear force along the bottom of the slice called S. There's a normal force called N. And so if you sum forces parallel to the slope, then you get S is equal to W times the component of W that acts parallel to the slope, which is W sine beta. This angle that W deviates from this perpendicular line is also the slope angle beta. And then likewise, if you sum forces perpendicular to the slope, this S does not factor in, and you get N is equal to W times the cosine of beta. And the weight of the slope of the block is the volume of the block times unit weight. And the volume is equal to L, the length, times this distance here, which is Z cosine beta. And then we assume a unit thickness in the direction perpendicular to the screen. And so we get unit weight of the soil times L, Z cosine beta. And therefore, if you take this W term and you plug it in right up here, you get S equals gamma LZ cosine beta sine beta. And likewise, if you plug this weight term in right here, you get N equals gamma LZ cosine squared beta. And the shear stress along that failure surface is equal to the shear force divided by the length. So the shear stress is S divided by L, and the normal stress is N divided by L. So we convert these from forces into stresses, and you divide those by L, and that L term factors out, and for the shear stress you get gamma Z cosine beta sine beta, and for the normal stress you get gamma Z cosine squared beta. And then we go back to our limit equilibrium equation for the factor of safety. It's equal to the shear strength divided by the shear stress. The shear strength is C plus sigma tan phi over tau. And then you basically plug in tau right here in the denominator. Sigma, this term goes right here. And we end up with our basic equation for the factor of safety, C plus gamma Z cosine squared beta tan phi over gamma Z cosine beta sine beta. And if you want to do an effective stress analysis, then there's a little bit different derivation. You get, basically you take the normal stress up here minus the pore pressure to convert this normal stress into an effective stress. and then we use C prime and phi prime, and everything else is the same. So you can use it either for a total stress analysis or for an effective stress analysis. For cases where the cohesion equals 0 and the pore pressure is equal to 0, then so this C term goes away, and of course the pore pressure goes away, so we end up with gamma z cosine squared beta tan phi, or gamma z cosine beta sine beta. The gamma z's cancel, one of the cosine betas cancel, and you end up with cosine beta over sine beta, which is 1 over tangent of beta. So the factor of safety for the case of cohesionless soils is tan phi over tan beta, which is the simplest equation for the factor of safety we'll see all semester. And so if you have, basically what this means is if you have a pile of sand, for example, with cohesionless sand, it is going, the steepest you can make that slope is equal to the friction angle. Because once the friction angle gets bigger than the slope angle, the factor of safety goes less than 0. And if the slope angle is less than the friction angle, then you can calculate the factor of safety using this term. So sometimes we call that the angle of repose. If you pile some sand up, you know, once it starts sloughing off, if you just were to measure that angle, you'd actually be measuring the friction angle of the soil. So yeah, you can do this on it's what they call the back of the envelope on your cell phone calculator, whatever. Super easy. Now, what if we have? Let's look more closely at some of the other variations of this. If you have non-submerged slopes, you can rearrange this equation to look like this for a total stress analysis. So now, you know, we're using the total strength parameters. And if you rearrange it like this, you can show that if the friction angle is equal to 0, then this term goes away. That's why we're rearranging it like this. And then the factor of safety is equal to this. Now, since it's submerged, we use the buoyant unit weight of the soil. That's why we have a gamma prime here. That stands for the buoyant unit weight. Now, finally, the general case for effective stress analysis can be rewritten to this form. And then, if you have a submerged slope, then it simplifies to the equation shown on the bottom. And we have C prime and phi prime and gamma z. So now we have all of the various equations we need for infinite slope, for effective stress, total stress, general case, submerged slopes. And we'll be applying this in our homework to a submerged slope, so you get a chance to apply some of these equations. And again, as I mentioned, this is it's a really common case we run into, and it fortunately has really simple equations we can use.